Welcome to the second episode of F-35 Lightning II, Busting Myths. In this episode, we intend to address additional myths and misconceptions that center around stealth, design compromises, engine reliability and cost. Myth number 5, stealth doesn't work. This is a complex topic but can be simplified. To begin with, radar is a form of electromagnetic radiation, like light or heat, and actually overlaps or consists of what we call radio waves and microwaves. The only difference between these types of radiation is their frequency, or wavelength of the transmitted energy. Within the part of the electromagnetic spectrum that radar sits, there are multiple bands of radar. The most common type is the X-band, which is used by fighter aircraft, radar-guided missiles and certain ground radar systems. Due to its widespread use, the F-117, B-2, F-22 and F-35 are all optimized to be stealthy in the X-band. In comparison to previous stealth aircraft, the F-35 is quoted as being a bit better than the B-2 bomber, which in turn was twice as good as that on the even older F-117. In addition, General Mike Hostage, who was previously commander of Air Combat Command, stated that the F-35's cross-section is much smaller than the F-22's. While the F-35 and other stealth aircraft are optimized for the X-band, many ground radars use what is known as VHF radar, which has a larger wavelength than X-band radar. What this means is that the emissions from this radar effectively ignore the shape of objects smaller than its wavelength, including some of the stealthy shaping on aircraft like the F-22 and F-35. These stealth aircraft do have features designed to reduce its radar signature against many different frequencies, including VHF radar, but due to the physics involved, are not yet able to achieve signature reductions to the same level as in the X-band. While this may appear to be a major threat, VHF radar and radars similar in frequency do have a critical flaw, in that they require significantly larger antennas. This is because in order to transmit or receive a certain frequency, you need to have an antenna sized to a certain multiple of the wavelength. This therefore requires low-frequency radars, which have much larger wavelengths, to be large in size, limiting or eliminating their mobility, and making them easy targets for long-range missile strikes. In addition, whereas an X-band radar can have hundreds or thousands of transmitters and receivers, allowing for a high-resolution track of a target, a low-frequency radar is much more limited in its number of TR modules and therefore cannot be used to guide a missile onto a fighter-sized target unless that target is within very close proximity. When an F-117 was infamously shot down in Serbia, it was shot down not because the low-frequency radar detected it at long range, but rather because the F-117 had flown the same route many times, had come within a few tens of kilometers of the radar, had its bomb bay doors open increasing its signature, and had no onboard equipment to realize that it was being targeted by an enemy. In contrast, an F-35 in the same position would have rapidly detected and triangulated the position of the enemy radar, and then been able to adjust its route to avoid it, or destroy it. It is important to note as well that stealth is not a binary feature, and that if future technologies do permit radar to track stealth aircraft, like the F-35 and F-22 from long ranges, then these aircraft will still hold an advantage over unstealthy aircraft, which will be detected even further away. Stealth technology is not at a dead end either, and so while radar systems will continue to become more advanced, so will the coatings and stealth features of aircraft, with technologies such as radar wave-bending metamaterials and electronic active cancellation being researched and developed to bring in the next generation of stealth. Myth number 6. The F-35A and C variants are compromised by the Stovall F-35B variant. Before the Joint Strike Fighter became a tri-service program, it was originally two separate programs: the CAF Common Affordable Lightweight Fighter and the JAST Joint Advanced Strike Technology Project. The CAF was designed to be a U.S. Marine Corps, British Royal Navy and United States Air Force fighter, that would be able to perform short takeoffs and vertical landings, like the Harrier, but with the option for the USAF to operate the fighter without a STOVL capability. This was the precursor to the F-35A and B variants. The JAST program, on the other hand, was designed to replace the U.S. Navy's Hornet fighters and the U.S. Air Force's F-16. This became the precursor to the C&A variants. However, when it comes to the design of the JSF, some claim that during the merger of the two programs, the Air Force was forced to adopt a fat aircraft, and the Navy were forced to take on a dangerous aircraft, due to the difficulty of creating a STOVL aircraft with more than one engine. These claims, however, are not true, as the fuselage is neither particularly that wide, nor is it dictated by the lift fan system. Rather, it is set by the size requirements of the F-35's internal weapons bays, and the aircraft size and weight, which are typically proportional to aircraft cost and relate to carrier suitability. The choice to operate a single engine is also set primarily by the cost-benefit of only having to maintain a single engine, and of being able to capitalize on the technologies developed for the F-22's F-119 engine, by having the F-35's engine, the F-135 a derivative of the 119. Myth number 7. A single engine is not safe for operation over the Arctic or ocean. This myth is based on the memories of older generations of aircraft, where engine failures were common, and it was not unheard of for a dozen or more aircraft to be lost annually. With the advent of computer-aided engineering and new materials science, engines have become significantly more reliable, to the point where in some cases, like with the Pratt & Whitney F100 PW229, the doubling of human error when maintaining both engines in a twin-engine fighter has resulted in a greater number of Class A mishaps, which are mishaps that cost more than $1 million, result in a fatality or permanent disabling injury to personnel. Specifically, over the past 25 years, there have been 5 engine-related Class A's for the F-15, and 0 Class A's for the F-16 using the same engine. When it comes to the F-22 and F-35, so far there have been 2 Class A mishaps for the F-22 since 2002, and 1 Class A mishap for the F-35 which occurred last year. This single Class A was the result when a rotating titanium part of the engine rubbed excessively against a polyimide strip, designed to be worn in after a number of flights, in order to maintain a very small gap between engine blades and the engine casing, increasing the efficiency of the engine. This problem is now well understood, with a set of maneuvers designed to carefully wear in the engine being applied now, and a manufacturing fix being introduced in the middle of the year. In addition to the improving reliability of engines, it is important to note as well that whereas older engines were prone to things such as fuel valve and igniter failures, the increased reliability of modern engines means that when they do fail, they tend to fail violently. What this means is that even if only one engine fails on a twin-engine fighter, it is very likely that the event will also cause the destruction of the second engine, or the destruction of secondary systems that the other engine relies on. Myth number 8. The F-35 is too expensive and concurrency is a bad idea. The F-35 is often called the trillion-dollar fighter, in reference to its total program cost, which will indeed cost approximately $1 trillion. But while this may seem like an outrageous number for a fighter, it is critical to understand that this value is the cost to research and design the aircraft, build 2,443 airframes and also pay for their fuel consumption, maintenance, spare engines, spare parts, upgrades and weapons expenditure from the moment the first F-35 flew in 2006, through to when the F-35 is scheduled to be retired, in the year 2065. In addition, while this level of spending is rarely heard of, this is due to the fact that the United States government nor any of its armed services has ever predicted the total program cost, including operating and support costs for any other fighter, nor has there ever been an official report into the total amount that has been spent on previous fighters. According to Lauren Thompson, Chief Operating Officer of the Lexington Institute, it would cost $4 trillion then-year to maintain the current fleet until 2065, rather than replace those fighters with the F-35. It has also been noted that if the U.S. economy maintains its current growth and average inflation rate, the United States economy will have generated more than $3 quadrillion by 2065, making the total program cost of the F-35, which will represent the majority of the United States air combat capability, to have been 0.03% of the United States economy's earnings. In terms of individual aircraft cost, the F-35 today in 2015 is currently in low-rate initial production, where aircraft are bought in smaller quantities. This is done to reduce the amount of retrofitting that may have to occur due to design changes during testing, which typically brings reduced efficiency in acquiring and producing materials and components required to manufacture the F-35. Despite this, the most recent LRIP lot of aircraft, LRIP 8, combined with the most recent F-135 engine purchase, Engine Lot 8, has resulted in the F-35A currently costing $108 million. At this current price point, the F-35A is already priced lower than the Dassault Rafale, Eurofighter Typhoon and F-22 Raptor. When the F-35 program completes initial operational test and evaluation, and full-rate production begins in 2019, an F-35A will cost less than $85 million, including the F-135 engine and inflation. This is approximately $25 million cheaper than the Rafale, and $40 million cheaper than the Typhoon. Additionally, while the program is over budget, another misconception is that the F-35 was meant to cost $50 million per aircraft. While this is partly true, it is often ignored that this was a very early estimate and was to be its cost in year 2002, which today in 2015, with inflation included, is $65 million. In comparison, an F/A-18 Super Hornet currently costs approximately $62 million, but provides a notably shorter range, payload capacity, electronics package and requires additional components, such as targeting and electronic warfare pods, to provide similar baseline capability to the F-35. One concept which often receives blame for these overruns is concurrency, which is where aircraft production and developmental testing occur simultaneously. The purpose behind concurrency is to bring forward the point at which an aircraft fleet, sufficiently sized for IOC, can be fielded, whilst at the same time maturing the production line and permitting a more comprehensive test program, with more test flight hours and test points. This allows the F-35 program to go forward as being the most complex fighter ever created, yet still be safely flown. The drawback to concurrency is that as problems are found and solved, revised or upgraded aircraft components must be retrofitted to more aircraft. So whereas in a program without concurrency, only half a dozen aircraft would require retrofits, now several dozen require these modifications. However, while some estimate these modifications to result in significant expense, it has been found that all concurrency-related costs have summed to approximately $2 billion, which represents roughly half of 1% of the F-35's procurement cost, or 0.1% of the total program cost. All other expenses that set the F-35 at a higher price point, to aircraft like the Super Hornet, are put into the procurement of its more advanced capabilities that make the F-35 a fifth-generation fighter. This has been another episode of F-35 Busting Myths. For more information, view the video description.